Hi everyone, in this video we are going to learn about logic gates, the basic building blocks of digital electronics. I will explain 7 important gates: AND, OR, NOT, NAND, NOR, XOR, XNOR gates. For each gate we will be going to look at its symbol, truth table and logic expression as well. These gates are used in almost every digital devices around us. So let's get started and understand how they work. As I said, you are seeing the slide. So that is every chip or microprocessor has to work on the basic building blocks. Those are logic gates. Basic building blocks of digital systems is our logic gates. So as we are saying logic gates, so what is meant by logic gate? So logic gate means two or more than two inputs or one input maybe. So output one or input, many inputs also. So a device, basically a device or a gate that performs a logic, whether it can be an addition operator, subtraction, any operator, but it has to perform some logic. So for that we are going to use some type of gates or the devices. Those are known as logic gates. This is the first one, that is AND gate. This is the next one, that is OR gate. So you can see observe the symbol as well. This is the next one, that is NOT gate, or we can simply say this is inverter. So this has only one input and one output. So these are the normal gates. With these gates we can build any type of circuit or any gates we need, or any logic we can able to build with these three gates. We will see one by one in the upcoming video, that is the individual gates and their truth table as well. So apart from those three, so we have called a gates called universal gates. So in universal gates we have two gates. So first one is NAND gate. The second one in the universal gates is NOR gate. So basically with these universal gates, that is NAND gate or NOR gate, we can perform any of the logic we want. So why we need universal gates? Already we have these three gates. So with these three gates we can perform any logic operation. But why these universal gates come into picture? So because assume a situation that any of these three we do not have, so we have only the NAND gate. So with the help of only NAND gate we can perform the same logic that can be performed with the help of these three gates also. So how this can be performed, so this discussion will be proceeded in the further videos. So in this video we are just going to focus on the gate, truth table and its output equation. So apart from this universal gates also we have another two gates. So that is first one is XOR gate. So the symbol is like you are seeing there, that is OR gate, and extra curve symbol is added. So we should not touch that curve to that gate. So this is known as XOR gate. So the next one in the list is XNOR gate. So basically the NOT operator is added to the XOR gate. So if a bubble is represented, that is NOT gate. So you are seeing there in the first column only we have NOT gate. So basically NOT gate is represented with a simple bubble. So the universal gates also, the NAND gate and NOR gate, are simple bubbled with the AND and OR gates. So I hope you can see that. So this XNOR also is simply a bubble. Bubble means NOT gate is added. So basically we will understand in the upcoming video. First let's discuss what is meant by AND gate. So basically all the circuits we may see may contain AND gate. So basically AND gate means the AND operation. So AND operation means A dot B dot operator, that is multiplication operator. So I hope you can see there, if two combinations means A, B, so we can have four types of combinations. That is both can be zeros, 0 and 1. So 1 and 0, and last combination is both can be 1. So let's see the truth table as well. So if you observe the truth table, so basically we have to draw two columns and one output column. Why? So because we have two inputs, that is A and B. So for the output column also we have to write A is equals to A dot B, that is the output shown with the diagram as well. So these are the four possible combinations out of two inputs. So the first combination is 0 0. So put this A and B in the output equation. So y is equals to 0 into 0. So we are going to get 0. So the second input is 0 1. So the output is 0. So the third input is 1 0. The output is 0. So the only output becomes 1 when the two inputs are 1. So that is the AND gate. The next digital gate that we are going to see is the OR gate. So basically it has two inputs, that is A, B. So in general case it might have 3, 4 and n inputs also. So but in general cases we are going to use only two inputs. So the output is the plus operator in between them, that is y is equals to A plus B. As you already see the truth table of the AND gate, so it is somewhat similar to the AND gate, because so we have 4 combinations as like in AND gate also. So the output will change, so we have to put the A and B correspondingly in the equation of y, and we have to get the output y and we have to put in the table. So these truth tables are very important in the logic gates. So according with the truth table diagram and with truth table, these two are very hard for the process. We are for the finding anything, we need to find truth table first. So the second is 0 1, that is 1, 1 0, that is 1, and 1 1, that is 1. If any of the input is 1, then the output will become 1. That is the main logic of the OR gate. Only it becomes 0 when the two inputs are 0. The next gate that we are going to discuss is NOT gate. So simply the NOT gate, also called inverter gate. Why? So if you are getting 0, it converts to 1. So basically it represents a simple bubble also, or the triangle form also, as shown there. So if 0 comes, it changes to 1, or 1 comes, it changes to 0. So the basically output equation as represented y is equals to A bar. So bar can be represented that comma with the hyphen inverted comma also. So both the representations of NOT gate are correct. This is the truth table of the NOT gate. So we have only one input, so we are going to write only one column. So the output is y is equals to A bar. So if 0 comes, it changes to 1, and 1 comes, it changes to 0. The 3 gates has been completed. So I hope you understood those 3 gates. So let's start the universal gates. So in universal gates we have only 2 gates, that is NAND gate and NOR gate. So with these two we can perform any of the operation that can be performed with the normal gates also. So these things, so NAND gate implementation as a universal gate will be going to see in the upcoming video. So in this video just we are going to discuss the truth table and its output equation. So if you observe there, that is the symbol. So the AND gate is just added with the NOT gate, that's it. So it is the next, that is the output equation. If you observe, so y is equals to A dot B, so and whole bar. So we have A dot B, we already saw in the AND gate. So the NOT gate is also added, so that we have to add the bar also. This is the NAND gate. In this video only we are also going to discuss the full diagram or the full circuit of the NAND gate. So if you observe there, so we have given with the equation, that is y is equals to A dot B whole bar. So A dot B, that is AND gate, so bar is there, that is NOT gate, inverter. So inverter of A dot B. So we are going to place the NOT gate in the input as A dot B, output as A dot B whole bar, as you seeing there. So this is the expression or expansion of the NAND gate. So if you observe the truth table of the NAND gate, so that is if both are ones, that is 0, if both are zeros, that is 1, and remaining 2 cases it is 1. So why this truth table is like this? So if you see the truth table of the AND gate, so if it's just opposite of the truth table of the AND gate, so that is NAND gate. So because in AND gate we are going to have A dot B, but in this case we just added NOT gate. So output also just flipped. NAND gate is just flip of AND gate. So the next gate we are going to see, that is NOR gate. So we already saw the OR gate. So OR gate plus NOT gate gives rise to NOR gate. So it is just simply A plus B whole bar. The output equation is just we are going to add NOT gate after the OR gate. As you seeing there, that is the expansion form of the NOR gate. So OR gate is added with the NOT gate. So the output equation is A plus B whole bar. If you observe the truth table of the NOR gate, so it is just the opposite of the OR gate. So if you just flip the truth table of the output of the OR gate, so you are going to get the output of the NOR gate. So in the OR gate, we are going to get 3 ones and 1 0. If both are zeros, then we are going to get 0. Again, remaining all the cases that are 1. But it is opposite. In the first, if you 0 0, so that is 1, because 0 plus 0, that is 0. Again, whole bar, 0 plus 0 whole bar, that is 1. And remaining all the cases are, we are going to get, that is as 0. So 1 plus 1 is 1 and 1 whole bar, that is 0. So in spite of the universal gates, so extra we have two gates. These two are very commonly used, so that's why we have made these two gates, so for the simplicity purpose. So those two gates are XOR gate and XNOR gate. So basically XNOR gate is the added not operator. So just we know XOR gate, so it's enough. So if you complement that, we can able to get the XNOR gate. XOR gate is also called exclusive OR gate. The output equation is given as y is equals to a bar b plus a b bar, or simply we can written as y is equals to a XOR b, as the operation shows there and the symbol is represented like that. So that is a basically OR gate like structure, and you have to a curve has to touch the two lines, and the output line. Why we have even described the XOR gate. So let's see how to describe, or with the help of the output formula, how we are going back the process. So with the help of reverse process, we are going to obtain the full circuit of the XOR gate. So the first addition operator is there. So for the addition operator, so first I am taking the OR gate. So the operators are a bar b and a b bar. So according to the input, so I am taking inputs, and output is the plus operator, so the main output. So this I have represented there. The next step we are going to do, that is inputs. So the two inputs are a bar b and a b bar. So those two inputs are to be merged with the inputs of the OR gate. So those two are produced with the help of AND gates, because in between we have AND operator, so dot operator. So with that, I have taken two AND gates with inputs a bar b and a b bar, so that I can obtain the product terms, that is a bar b and a b bar, with the help of AND gates. So those two are the outputs of AND gates and the inputs of OR gate. So I am going to merge both the outputs with the inputs of the OR gate. So this is the final circuit. So even though if you want a bar, so that is simply the a is coming, you can take the NOT gate, so that becomes a bar. So I hope you know how to get b bar also. The b bar is coming as a normal line as a, so you can take NOT gate, so you are going to get b bar. That's a simple one. So this is the final circuit. So these kind of circuits we will see in daily many of the applications. So to reduce the circuitry or to minimize one, so we have obtained the simple formula, that is a XOR b. So this format we have to remember or recall in every circuitry while doing, because this kind is very familiar. So we have to use so we can simplify that. So the above circuit or above the symbol is the minimized one for the down one. Let's see the truth table of the XOR gate, and we will finish this XOR gate. So if you consider this one, so we are going to get the truth table as the same four combinations only. We have, because we are only having two inputs a and b, so we are going to have the inputs 0 0, 0 1, 1 0 and 1 1. So the output combinations would be, so if both are same, then 0, both are different, 1, same, 0, different, 1, same, 0, different, 1. So remember this, because if both are zeros, 0, both are ones, if same, so same bit a and b, so then you are going to get the output as 0. If both bits are different, you are going to get 1. Why? So because we are going to apply in the formula individual digits, and we are going to check that. So to verify the truth table, we are going to put the 0 0, 0 1, 1 0 and 1 1 in the equation, that the main equation we have derived, and circuit also we have derived. So this symbol is the shortcut symbol for the above circuit that I have mentioned, or we have derived from the equation. So if you observe there, so I have put all these things. So 0 0, 0 1, 1 0 and 1 1. So we are going to obtain 0 1 1 and 0. So put those outputs in the table. So hence verified from this given by putting in the expression also. So I hope you understood all the circuit diagram and the symbol and the truth table, you have to by heart the truth table, or you have to know by heart the truth table, because that's very important truth table. We are going to use the truth table for the gray to binary and binary to gray code conversion as well. So if you see the XNOR gate, so now we are going to start the XNOR gate. It's just the invert of the XOR gate. So you have to add a bubble, so that becomes XNOR gate. So the full form of XNOR is exclusive NOR gate. So the symbol is same, so you have to add bubble. So the output equation is A bar B bar plus AB, or you can represent A, so dot circle B. So this is the representation of A XNOR B. So you can see the difference. In the circle we are having bubble, but in the XOR gate we are having plus. So you have to observe the difference in the representation of the output. So the main equation is top one only, but this is the simple representation that we can use. For this XNOR gate also, we are going to build the full circuit. So this is just the symbol of the shortcut one. So this is also we are going to use in our day-to-day life very much, very often, very familiar. So for that purpose only they have decided to make a shortcut symbol, so for daily usage. So this shortcut symbol can be used. So this for the shortcut symbol only we have a truth table. So if we have encountered this kind of things, so we can apply the simple truth table, so we can get the outputs very easier without doing the much calculation or without solving the bigger circuits. So if you want to know what is the full circuit of this XNOR gate, so you are going to trace back the full circuit, or we are going to expand the output equation, so that we are going to obtain the full circuit. So in between we have a plus operator. So plus operator means we have OR gate. So the operands are A bar B bar, so and AB. So I am taking in the two inputs of the OR gate, and the output is the final output that I have shown there. As we saw in the XOR gate, in this also we are going to take the two AND gates. Why? So there are two product terms in the input of the OR gate. So for that purpose only we are going to take two product terms. So how we can get the two product terms? We can have two product terms with the help of two AND gates. So I am taking first one is A bar B bar, so that we have to take with the help of one AND gate. So second one is product of A and B, so for that also we can take the AND gate. So you can see there I have taken with the help of A bar B bar in one AND gate and AB in one AND gate. I hope you can relate this one with the XOR gate, and you have to just merge the output of AND gate with the input of the OR gate. So after merging we can get the final output. So this is the circuit. So these circuits are very often very familiar. So for that we are minimizing this circuit, and minimized circuit has to have some symbol, shortcut symbol. So this is the shortcut symbol we are going to use. So that is XOR. So for that XOR also we are going to have a shortcut symbol, that is A XOR dot operator. So circle is there. So B, that is A XNOR B. And what is the main difference between XOR and XNOR? So if you observe there, so you can also see, so that is A bar and B bar are in the same product term. So that is the main difference in the XNOR term. So you can also write, so that is A XOR B whole bar. So that is also a valid one. So you can also write one. So because this is a simple inversion of the XOR gate, so it is not a problem to write A XOR B whole bar. So that also you can see in the slide also. And finally, that we are waiting for, that is the truth table or the XNOR gate. So it is the just inverse of the truth table of the XOR gate. Why? So we are just inverting the output of the XOR gate. So that is our XNOR gate. So in the XOR gate I am said that we are going to get if same bit, that is 0. So that is for 0 0 and 1 1 as well. So the output of XOR gate is 0 1 1 0. So if just invert them, we are going to get 1 0 0 1. So this is the output. So you can also verify with the help of the formula, that the formula if you put 0 0 there, so you can get the output. So if you put in place of 0 0 in A and B, so you are going to get 1. So like that only if you put 1 1, so you are going to get 1. So this is the final outputs of the XNOR gate. So this is the truth table of the XNOR gate. These are the things that has been done in this class. I hope you understood all. And I forgot to mention a note that, so AND gate and OR gate, So not only they have only two inputs, they can have multiple outputs. But as I said in previous slide only, so those are the regular use or familiar use, so we will be going to use them daily, or we will be going to use very regular. So these are the three input AND gate is very not used very commonly. So but we can also perform the same operations that A dot B if two operands are there, if three operands are there, A dot B dot C, if n operators are there, so you have to multiply all them with n up to n. So the same with the help within the OR gate also. So if you have given with A and B, just add A and B. So if you are given with A, B, C, so you are going to add C up to C. So up to n, then you have to going to add up to n. So they can give how many they want, but the main thing or the main use in the markets are just two input AND gate and two input OR gate. Thanks for watching up to now.